specific ice, water, and steam. And for the questions I believe I asked you, I tried to double check. I don't think you need the specific heat capacity of ice and steam. They give them to you in the book for water, but it's not that clear. So for those of you that are interested, so for ice, water, steam, so this is when heat's going in or out. Say you're trying to heat up some ice. You know, it's negative 40 degrees Celsius, and you're trying to heat it up, and you need to know what seed to put in to know, if you're curious, how much heat it'll take, or you know how much heat, you want to see how hot it gets. We did that at the end of class. We took it from negative 50, and I used a half. This is for if you're using grams and calories, because that's what the book is using, grams and calories. For water, it's 1. That's the one they talk about a lot, but they never explicitly say, oh, the specific heat of water is blah, blah, blah. They keep talking about, if you have 1 gram of water, because that's the easy way to remember this. If you have 1 gram of water, you want to raise its temperature 1 degree Celsius, it'll take 1 calorie. Isn't that convenient? So 1. Works out great. For steam, it's a half. These are approximations, but pretty close enough approximations. That's what I use. So I wanted to give that to you because some of you were curious. Do you have any questions in general about phase changes? You know, I know you went home and thought about this on your ride home and over dinner, and something was, but give you a chance.
You mentioned that evaporation takes away energy.
Evaporation takes away energy.
When it's going from liquid to a gas.
Yeah, liquid to gas is evaporation. Yeah, it takes energy to change from liquid form to gas form. Yes.
Is it absorbing heat from something, or adding heat to the environment that it's going to?
Let's say you got let's picture 1 gram of water, liquid form, and it's going to convert to 1 gram of steam, gas form. In order to go up, I like to think, to the right as I've been drawing it, it takes energy. That means energy is going to have to be going into the system, the 1 gram of water. It's going to need to absorb 1 gram. Let's say, I'm starting to put numbers in. That 1 gram of water needs to absorb energy in order for it to change into steam. So it's taking the energy in. Yes. So in that sense, I like using the 1 because I think you can relate better. And remember, he said hot asphalt, you spray water on it. As it evaporates, that cools the asphalt. Absolutely. Just like water on you. Your sweat, liquid, salt water. As it evaporates, it's taking energy from you. Because the water needs to absorb energy to get converted. Where does it get that energy? From you. So it takes that energy from you, absorbs, goes to steam, leaving you with less energy, conservation energy, and so you get colder. But the environment gets warmer. Yes. Good question. Anything else bothering folks? All right. Well, condensation, same idea. That's going from what to what? Just checking you. Gas to liquid. Back in. So if the steam condenses back into liquid, in order to go that molecule of water, gram of steam to gram of liquid water, it's got to give up energy to... So I'm only hearing you half. What number is it? And I can read too. We are warmed by condensation because water molecules in the air that strike our bodies, blah, 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 blah. gain kinetic energy as they change state, transfer some of their kinetic energy to us, or form an insulating layer on our bodies? And you think the answer is? Transfer some of their kinetic energy to us. I don't mind telling you that's correct. We are warmed by condensation because water molecules in the air, gas state, vapor, they strike our bodies. What do the molecules themselves do then? They combine, and because they... Let's see if anybody can just get it. Well, who's moving faster? Water molecules or water vapor? The water vapor is moving faster. Yeah, so that's it, Kate. So when they run into you, they're transferring some of their higher kinetic energy to your lower kinetic energy ones. So they slow down, and yours speed up. Yeah. So they're releasing the energy. Yeah, and if they were to gain kinetic energy again, they could get converted back into vapor. Yes, absolutely. Energy is always conserved, but they can change phases in addition to just changing their temperature. And that leads into thermodynamics. That's what it is. It's the transfer of heat back and forth with mechanical energy and how we can use it to do work or to do work to move heat around. That's when most people think of heat and temperature the way it is. How is it useful? Well, that's the whole point of Chapter 18. And I feel we have a very good foundation now to, I hope this chapter will be less confusing than the others. To me, if we started with this one, oh, what the heck? And it would have seemed really difficult. It was for me when I first went through thermodynamics. I won't lie. I hated it. So, I wrote down thermodynamics. It's in your book. Study of heat and its transformation to mechanical energy. We've been studying heat this whole time, but now let's turn it to mechanical energy. See how it's useful. And I like thermodynamics in one sense because it was developed before molecular theory was created and discovered, understood. So you remember the overhead projector with the little BBs oscillating, and we think of billiard ball physics? We just did the example, the molecules slowing down. Well, they didn't picture it that way. They didn't look at it microscopically because they didn't understand that yet. So they looked at it macroscopically, the big picture, end results. Well, this has more energy. I don't care how it got there, I just know it did. So it's based off two main things. Conservation of energy, which we're totally familiar with now, right? And the fact that heat flows in which direction? Hot to cold. That's how it does it naturally, spontaneously. That's essentially, we just covered the first law of thermodynamics and the second law of thermodynamics. But that's what the rest of the two lectures are me babbling about, so you understand them even better. But that's what they're based upon. That's what they recognized. Before I go there, I'm going to show you this. I have two thermometers. This one out here in the open air, it's at 19, 20 degrees Celsius. And this one's stuck inside this styrofoam little bin. I just put plastic on the top, so it's enclosed. Messed it all up. Okay. And it's at 20 degrees Celsius. Well, I'm going to turn on a 300 watt bulb, and what's going to happen? They're both going to heat up. Let's start with a bulb. What's it do? It radiates. Very good. See, radiation. Yeah. It doesn't need the air to do that. And so both of those will absorb the light's radiation. It's going to emit visible light, but it's going to emit heat too. 300 watts is hot. You can put your hand here and you can feel it. And I can stop babbling and turn it on. You can start watching. All right. That radiation goes to both of them. Then what happens? They absorb that radiation. Does it stop there? Yeah, they emit as well. Very good. And so we're trying to find a balance here. How is this one? It gets hot, and so it just emits. And where does its radiation go? Yeah, out into the room. It can heat up the air too, and we can get convection. So it can cool by convection and radiation. How about this one? Yeah, it gets stuck in the box. It can convect inside the box, but that air is going to heat up a lot faster. And so convection won't help cool that one as much. And this is the greenhouse effect that we discussed before. This has energy, radiant energy going in. It absorbs it. Do you think that thermometer is as hot as the bulb? No. So who emits more energetic light waves? The bulb. Yeah. And do they have shorter waves or longer waves? Shorter. Higher frequency, lower frequency? You guys are getting it. Very good. So they come in, starting to heat that up. It radiates its own, but they're longer waves, lower frequency, less energy. They can't get out of the box. They're reflected back in. And so it traps the radiation too. Shortwave radiation comes in from the sun, heats up the earth, and the earth emits longer wave radiation that the atmosphere can trap. Greenhouse gases, you've heard of these? Global warming. And let's see, you can tell already, that one's at 27 degrees Celsius and this one's at 21. So they're both heating up, but this one's getting hotter more quickly because it's not being cooled as fast. They're both absorbing and emitting, but this one is absorbing more than it's emitting. Yeah? I know what you mean. Absolutely. As this one gets hotter and hotter, it emits shorter and shorter wavelengths. Yes. Yes. Although relative to the bulb, they're still pretty long. But yes. Anything that gets hotter and hotter emits shorter and shorter wavelengths, has more energy. We'll let that keep running. Clicker time. I found some questions I think will help review and lead us into thermodynamics. I still remember what it's like after spring breaks and my brain's still not going, so I'm going to open polling to some few questions. Help us review some things. Make sure we filled in holes because I really want this thermodynamics to just click. So, polling's open, channel 44, answer away. This was good. Some of your initial questions might help jog your memory of what this answer should be. When evaporation occurs in a dish of water, the molecules left behind in the water are what? Ten, 9, 8, 7, 6, 5, 4, 3, 2. Thanks for committing. It's been proven. You learn more if you commit to an answer. So when you see the answer, whether you're right or wrong, you'll learn more. 2, 1, 0. Okay. Overwhelmingly 77% D. Oh, I'm so proud of you guys. That is correct. Yes, the water molecules, okay, evaporation. They're moving around. Remember the particle theory here? The ones that have enough energy escape. So the ones left behind are less energetic, A, which means they have decreased average speeds, which tells me they have a lower temperature. So all of those. Does that make sense to those of you that didn't answer it? The ones that stay in there do stay where they were. Which ones escape again? Yeah. So who's left behind? Just like they were, but who are they?
But they still are.
Correct. And that's exactly right. The more energetic ones are the only ones that can escape. So they leave, leaving the less energetic ones behind just as they were.
But theirs weren't lowered.
No, they weren't.
Stayed.
But if you have a body of water that's at, say, at 20 degrees Celsius, and a whole lot of it evaporates, What's the temperature of the body of water now? Yeah. But the molecules that stayed behind they're not slowing. They didn't slow down anymore, but they don't speed up either. It's the ones that was bringing up the average. Those of you that are getting 100% on the tests, bring up the average. If we got rid of everybody that gets A's, then the average is lower, isn't it? The temperature's lower. We didn't change you guys. You're still getting B's. But,
Yeah, I understand. I was just thinking of each individual
It's a good point. Could be worded better. I'll note that. Yeah, it's a good point. Let's do another one. Yeah, if you look at the individual molecules. Yeah. Well, that's why you still get credit for answering it. And now we've learned. All right. Next. I hope you get this one, Kiva. We just discussed it. I like these questions because it's the change. So when something's changing and happening, and that's the kind of the key to thermodynamics. 10, 9, 8, 7, 6, 5, 4, 3, 2, better get your guess in, 1, 0. Oh, we're split, 49% B and 42% C. So you guys are kind of split. Well, that's fun. That's when I like, okay, talk to your neighbor. Let's see who convinces whom. We'll do it again. Polling's open. And I won't lie, this one, it's not quite as straightforward. That's why I'm asking it. Clearly. But this will be fun to see who was able to convince whom. 10, 9, 8, 7, 6, 5, 4, 3, better hurry up, 2, 1. Some of you don't want to vote again. Now you're not sure. Okay, we have 58% on C now. So more of you went to C, which is the correct answer. Relatively slow-moving molecules condense from the air. That means they coalesce. Let's picture, they condense on you, let's say, so you can relate to it personally. If they do that, who do they leave behind? The faster ones. The cooler ones are the ones that are able to coalesce. Or when they collide with you, it slows them down enough that they can stick and coalesce and condense and become liquid. That leaves the more energetic ones behind in the air. So it actually increases the temperature of the air. That's like, to relate some more, the shower. You put a lot of water in, you close the doors or whatever, and there's a lot of water vapor in the air. As it condenses, it keeps the room warm. That's how you can remember it. At least, and then you can work backwards and think, okay, it keeps it warm. I know the answer now. Now why? Because the slower moving ones, they either get slowed down or are slower down, and they're the ones that are able to coalesce, leaving the more energetic ones behind. Was that you, Ennis? Yeah.
Now, that makes all the sense in the world. But on my first question,
Uh-oh, did I say something wrong earlier?
no, you're right. With evaporation, it cools, let's say water on a surface cools the surface and transfers that heat into the environment. Condensation is the opposite, you would think, where the moisture that has evaporated is condensing now.
Yes.
And the answer here is that it's increasing the temperature still.
Of the air.
Right. So evaporation increases the air temperature.
The evaporation increases the air temperature.
Taking heat from the ground and taking it into the environment.
The more energetic molecules are the ones that left, leaving the liquid and the surface colder.
Right. And the environment, the air, warmer.
Did I say that earlier? Shame on me. Let me rephrase then, because I said it wrong. Let's go back to that liquid. It absorbs energy, make sure I get it right this time, energy from you. It needs that energy to get converted to vapor, to gas. That individual molecule has more energy now. It went into changing phase. It's not. It itself isn't hotter. Remember, while you're changing phase, its temperature, the energy went in. So you're cooled because it took energy from you. I should not have said it went into changing phase of that water to get it to vapor, gas.
Does it have any effect on the temperature of the environment?
It does not. It should not increase the room temperature until more energy is added to that and speeds them up. I apologize. So there, the energy goes into the water to change its phase, cooling where it was at, because it took energy from that. When it's condensing, it's giving up energy to get down, and where that energy goes into the air. You can think of that, leaving the more energetic ones behind. Did I clear it up?
Is that how morning dew or the
Morning dew, homework question. Yep, that totally answers that question. What was next? Yeah, I'm going to ask this one. Go. Got your water just sitting there on the table. Which processes occur? I'm not going to give you as much time. Let's see what your gut says. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's a couple of you who haven't voted yet. Keep going. I haven't closed it yet. Too late. Okay. Most of you think C, both of them. But a lot of you think just evaporation. The correct answer is both. If it's just sitting there, there's no reason both can't happen. I didn't say what's happening to it. Let's say eventually all the water disappears. Then evaporation is dominating condensation, because eventually all of it will be gone. If condensation were dominating, you'd end up with more water. But they're both happening. If it's open to the atmosphere, then those molecules, the high energetic ones can escape, and the energetic ones that come in and run into it can slow down, and if they slow down enough, they can coalesce and condense. So both are always happening. If they were both happening at the exact same rate, we would notice what? Nothing. It would always stay the same level. It'd never disappear. It'd never seem to get bigger. This is a long-term thing, But most of the time we see things disappear because the air usually is never 100% saturated, which means there's more room for water in the air. And so evaporation usually dominates condensation when we just leave water out. But both are happening. We answered that one. All righty. Now you, yeah, that's the relative humidity. It's the rate. The absolute humidity is kind of like a density. How much water vapor per volume is in the air? Okay. How much can it hold at that temperature? And then they do a ratio, a percentage. Oh, it's 50%, 40% relative humidity. That means the air can hold 60% more water vapor at that temperature. All right, I'm going to open polling. Oh, dang it. Well, no, that was right. Sorry. Carry on. Thought I hit the button and you guys already voted. Think this one through then. What does boiling do to the water itself? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. C is the majority, 57%. Both warm and cool the water at the same time. Tell me why. Somebody said that.
Because, like, if you've got a big pot of water and it's boiling, the molecule at the bottom is going to heat up and rise, but as it gets to the top, it's going to cool back down and fall to the bottom. So when it happens on a large scale, the average temperature is staying the same.
Ah, yeah, okay. So the water at the bottom gets hotter, comes up through convection, cools. So yeah, you get some convection there. If you leave it on the stove, do you expect the overall pot to get hotter or colder? So I put my pot of water on the oven, I turn it on, it'll never, and it gets to boiling.
Well, it will
It's now boiling.
evaporate out and disappear because it's getting hotter.
So include that in your answer now.
Well, the water doesn't change temperature, but the steam does, doesn't it?
It'll go from 100 degrees Celsius water to 100 degrees Celsius steam through the latent heat of vaporization, as it, that 540 calories per gram. Yeah. Then once it's steam, if you keep applying heat, yeah, it'll raise its temperature. But yeah, that steam disappears. So if some of this liquid is evaporating, that's what a boiling is, just under the surface, some of it goes away. And the water that's left behind, and the correct answer is cooled. This one's counterintuitive, but it's that same evaporation thing. Boiling is evaporation just under the surface. So the water itself actually cools a little. Because if those energetic ones, it takes energy to convert them to steam and then they leave, then it's leaving behind less energetic ones. Still at 100 degrees C, and you got to go through the phase change. But yeah, it actually kind of cools them a little. So why doesn't it drop? Why when we see water, does it not? It gets to 100 degrees Celsius, it starts boiling. Why don't we see it drop? Because we're still putting heat in. So it's evaporating, boiling, but heat's coming in, and they're in balance while it's boiling. But the water itself, it's actually a cooling effect. It's very slight. We're not going to notice it. But I wanted the author had this question. I chose it because doesn't that seem very counterintuitive? I mean, I won't lie, it does to me. But does it make sense? If you include the fact that they go away, just like evaporation, it's going to cool what's left behind.
Does the change of state actually begin when the molecule is down below because it forms a little bubble?
Yeah, in boiling, the change of state does start down there because it gets vaporized down there.
Bigger and bigger, and then finally, so
Yeah,
that's how I understand.
that's correct.
Why it gets cool. Because then when it leaves, because it was hotter to begin with, and when it leaves, what it leaves is cooler.
That is true. The result is the same. It does leave it cooler. It does start vaporizing underneath down there. And if that vapor pressure is enough, remember we talked about it can sustain itself and the bubble will grow. It rises because it's less dense. The pressure's less. It expands because it has less water above it. And yeah, it gets to the top and that vapor leaves, which has a slight cooling effect on the water it leaves behind.
And the reason a pressure cooker raises the boiling point is because pressure doesn't allow the bubble to leave.
Yes, pressure cooker exerts more pressure. Yeah, the bubble can't form. It needs more vapor pressure. the vapor needs more energy to sustain itself, to keep boiling. So that won't happen until the whole thing's at a higher temperature. All right. Good. Well, I hope that getting you thinking. Let's turn that off. Because you learn this stuff, and from some comments and things, I'm not sure you were processing it. So, let's see how this is doing. Oh, wow. 27 degrees Celsius. So it's definitely hotter than you are now. But that one's at 56 degrees Celsius. Uncomfortably hot inside there. I wouldn't want to be in there. I'll turn it off. And we can watch. Because now it's trying to cool. What are ways that it's going to try to cool? The 3 ways of heat transfer, right? Conduction, convection, radiation. Does this thermometer conduct heat away very effectively? Why? It's trapped in there, more specific, for conduction. Remember how heat transfers through conduction? Yeah, well, it's actually foam. But that's the point. It's insulated. Yeah, and so, well, it's hard to see for you guys, but it's just kind of resting in there. It's only touching air, and air is a poor conductor of heat. It's touching the styrofoam over here, and the air inside that's warm can't conduct through the walls of the styrofoam as easily as it can if they weren't there. So that's conduction. How about convection? We discussed it. Yeah, the air is trapped, so it can't warm this air out and lose energy. And radiation, because it's longer wave, relatively speaking, and it stays trapped. It's reflected back in. This is exactly this is our weather. This is how the Earth does it. Heat can be added. You can think of the Earth as a big heat pump or refrigerator, depending on which way it's going. Heat comes in, it heats up, it radiates its own. Some is trapped. It's trying to conduct it away. It creates convection. We get our weather. Pressure differences make it move. Temperature differences make heat flow. And if you meteorologists have to understand everything you guys have just been studying, or as confusing as weather is to predict, it'd be even worse. All right. That's the wrong side. You know absolute zero. We know internal energy, blah, blah, blah. We can do the first law of thermodynamics. And it essentially says, the book puts it as, whenever heat is added to a system, it transforms to an equal amount of some other form of energy. It's conservation of energy. So if you have a system, and I haven't used a term for it yet, but internal energy in physics is quite often uses a U. So that's what I'm going to use to represent internal energy. Remember, that's all the energy, not just the average translational kinetic, but all the energy it has internally. Any kind of motion, molecular bonding, and all that kind of stuff. If we add heat, this should make sense to you. What can happen to this system? What's one thing that could happen? It could rupture. Yes, its internal energy would increase. Yeah, but see how energy is conserved? What else could happen if you were to sit under this lamp and you're the system and we're adding heat to you? We could rupture. Our internal energy can increase. What else could happen? Say again? Perspire. Yeah. And basically because you got hot. Heat's flowing from the hot to the cooler. Heat can flow. In order to perspire, your body is going to have to do work. So one thing that happened, this thing can do work. This work done by the system. That could happen. But you see, energy is still conserved. And so, if you put heat in, heat that's added, that can have a couple effects. It can change the internal energy. It would increase it if you add it. And or it can make the system do work. If this internal energy increases too much and it explodes and ruptures, that means the system just did work. But if you account for those forms of energy, it all makes sense. That's the whole point of the first law of thermodynamics. It's conservation of thermal energy. I so wish somebody would explain. Maybe they did in my class explain it this simply, but it just did not click. All I saw was a bunch of charts and graphs and things I had to go find, and I didn't get it. Hopefully I'm helping you. Plug that in. Conservation of thermal energy. Both heat and work, do you remember they're similar? They represent forms of transfer of energy. We don't say an object possesses work. It has the ability to do work or be worked upon. Same with heat. Something does not possess heat. Oh, that contains heat. No. It contains internal energy, which gives it the potential to be able to do work or be worked upon. It transfers that energy. Heat and work are forms of transfer of energy in or out of a system. You can do work on a system, couldn't you? We could put work into this, but energy is still conserved. Instead of adding work here, we'd subtract it, right? It'd be work on. You do have to pay attention whether the work is going into the system or out of the system. But if you think of it that way, you can remember. Because usually when you see this on the internet or something, first law of thermodynamics, they give you a bunch of these formulas and everybody kind of rearranges them. And some does add, some does output. Some do by the system, some do on the system. Physicists like to look at it differently than chemists do. And I get really confused which way to write the equation. But they're all true. They're all saying the same thing. And there is no contradiction. Because if you put work into the system and you add heat, they're both going to make this raise. And they all should balance, right? These go in, that's the amount of change. If all are happening at the same time, the ins better balance the outs. You follow? It's conservation of energy. So back to my point with microscopic and macroscopic. They didn't understand the particle theory. See, we're just interested in what happens. We see the work done, or the work we put in. We see how much it rises in heat. Temperature is a measure of that. We can gauge all this. We don't have to know what all the individual molecules are doing. That's what thermodynamics is not interested in the detail. It's more interested in the overview. So I'm warming up a steam engine over here. This is like a heat pump. It's where you can actually make all this stuff useful. Let's do some work and drive something. So I got water in here that's heating up. So we're applying heat. What's happening to the internal energy of our system? It's increasing. And if it increases enough, we ought to be able to use that to do some work, right? Okay, our tea's ready. So I'm going to close off the valve and open it up over here. The steam's going to come through here. This was at room temperature. It's going to have to transfer some energy to it to heat it up. And on the back side, in here, there's a piston. It can rotate. And so once the steam gets in there and heats it up, this thing ought to be able to be driven. So we add heat. We can increase the internal energy of the system and or have the system do work. But the energy is still conserved if we measured it all. Yeah, Kiva? In this case, I'm adding heat. It can do both. Remember, one part of the internal energy, one part is that average translational kinetic energy, and if that's increasing, yes, the temperature's going up. But remember, if it's just changing phase, it's not changing temperature, but it still goes into increasing its internal energy. So both can happen. And temperature's in with that. We'd have to melt it first, then raise it up, yeah. This is, now the steam is what's coming over into here. And let's see if there we go. give it a little jump start. And the steam engine was a great invention. But it was just conserving energy. Somebody decided, hey, if we put heat in, we can store a lot of heat in vapor. You saw why, because it takes a lot of energy to get to gas form. Well, can we use that now? Instead of just increasing the internal energy, can we have the system do work and transport us around or something? Absolutely. But you're not going to get any more out than you put in. Energy is conserved. You just drive away. The way this works, I know it's a little small, you might not be able to see it, but you get a piston going back and forth. That's essentially what's happening in here. It's going up and down. So I guess we're like this. Whatever. And just through some clever valves, when it goes this way, it gets about here. And if you think a steam can come in, there's through an opening in the middle. Steam comes in over to here, this side, and the steam does work and makes it expand, drives the piston. Its momentum carries it back a little bit, and now the valves are switched, so that steam went out and new steam comes in. It can now get to this side, expands, does work driving it this way, pushes it out, drives. As new steam comes in, and the steam's constantly doing work on the piston. That's what the rudimentary basic steam engine is. So think of steam coming in and doing this, not me. And it would be going and driving your wheel. Ow. Do you have a question, Kate? So if we added let's say 100 joules of heat to a system, and we see that the work done by the system is 40 joules, then boom, we can say what about the internal energy? Yeah, it increased by 60 joules. It must. That's the first law of thermodynamics. You can be given any of the two and get the third. Let's say we did work on the system of 40 joules. What happened to the internal energy? 140. Because Q was added to the system, and we do work on the system of 40, then the internal energy must go up 140. See, this one, where the work done by the system, this one comes in, this one goes out. You just got to keep it all conserved. If you keep that mindset through it, you'll be able to work out any problems. Yeah. In the system. So, for example, the steam. Say we put 100 joules in the steam, and we measure the piston doing 40 joules of work. Then that means the steam must have increased its internal energy by 60 joules. Because we're not getting it out as work, and I know I'm putting that much in, so it must go into increasing the steam's internal energy. And if it's not changing phase, it must be increasing its temperature. Yeah, you can increase the internal energy of anything. Yeah. Here, I'm making up the number. Let's say it was 1 gram. Well, I don't know that. But the point is, let's say we put 100 joules in. Let's say that's enough to boil some of this water so that we have steam to do it. If we're only getting 40 joules out, though, of work, then 60 of those joules went into changing the phase of the water to steam and or raising the temperature of the steam. Because it needs, because 40 of these joules is coming back out. So the net increase of the internal energy of that water and steam, the system, must have gone up 60, period. And again, microscopically, I don't necessarily know what's going on in there, but it has 60 more joules of energy internally If I put 100 in and I'm only getting 40 out, it's in there somewhere, somehow, whether it went into boiling or increasing a temperature. Remember, both of those are in there. Let's do 2 more demos and call it good, because we have just enough time. Adiabatic. Your book talks about adiabatic. And what that really means is just if you do it fast enough, compression or expansion, let's say the steam's doing work, it's trying to move thing around, then that's work on a system or work done by the system, and so there can be an increase in internal energy or heat flowing in or out. Adiabatic means it generally happens so quickly, no heat flows in or out. So there's going to be no change in Q. If you do work on a system, what happens to its internal energy? If no heat flows in or out, it must, and vice versa. If the system does work, but no heat is flown in or out, then the system's internal energy must decrease. That's adiabatic. So I have 2 examples. We did one before, if you remember. I put some water in here. It was warm water to warm it up, so I won't have to pump as long. All right. I'm going to do work on this system by pumping on it. Not that. Little stopper. Seal it off. All right. Can you see? I'll get behind, I guess, so that you can see. So I pump on it. Hey, I'm doing work on the system. So its internal energy is increasing. This is not adiabatic because I'm kind of slow. So I expect its temperature to be going up too. But at some point, watch it. Do you see the condensation inside? Well, what it did that was adiabatic. It was quick. The gas just expanded. The pressure got so much, it did work and blew the cork out. And then it could that air and a lot of water vapor in there could expand. It cooled and did work. That was adiabatic. Another version is the fire syringe. I'll do it over here. This one, I'm going to compress quickly. That one we released, expanded quickly. This one I'm going to compress, and we'll be done. Little flash paper. It's cotton, essentially impregnated with oxygen. Magicians use it in their palm when they make the flash, whoosh, and it doesn't burn them because it burns so quickly. But basically, it's cotton. It burns at a higher temperature than room temperature. One little piece I'll put in here. I'm going to seal this off. And then I'm going to slam this piston down so that it quickly compresses the air inside. So I'm going to do work on the system. If I do it fast enough, no heat essentially flows in or out. So all my energy of work goes into increasing the internal energy of the system, which will raise its temperature. And if it gets above its flash point, it'll ignite. So I'm going to turn the lights off. It's a little bit more visible. Watch right down here. You ready? Adiabatic. No heat went in or out. All my work went into increasing its internal energy. Part of that raised its temperature above its flash point and ignited it just by thermodynamics. Thanks.